Yeah, and the people that are being used for
Hey everyone, hope you guys all had a nice weekend. I'm going to start off today by pointing out under day date. So we're going to be going over the test review worksheets. I have a couple of them, so but I'm going to be kind of jumping around based off of kind of hitting the topics that we haven't seen in a while. So we'll look at that. I don't think we'll be able to get to the curve sketching. Oops. The curve sketching implicit problem today. So we're probably going to come back to this as another practice problem for the next day or two. I'm going to go over test topics. Still a little bit tentative, but if there's any changes, I'll let you know tomorrow, but I'm pretty sure these are going to be what we're going to be focused on. Summary notes from class. So I've been kind of showing these quarter sheets, and some students were asking, can they just print this out and they can just use it on the test, and that's perfectly fine. There's one more thing I want to update though, so I'm going to probably make an addition to this this afternoon, so you guys can feel free to print this out tomorrow or next day and have this available to you when you're taking the test. And then also, if I have time tomorrow, Wednesday, I'll also go over some common mistakes that I've seen on previous quizzes and tests. For this year, we're only taking Chapter 5 tests because of our condensed schedule. But previous years, I've had 2 quizzes leading up to this Chapter 5 test, and I've seen a pattern of mistakes that students make, and so I kind of compiled it into a document that I think hopefully will be beneficial. So you can read through this, or I'll be able to hopefully go over it tomorrow or Wednesday. So just things I've seen in the past, patterns I've seen that students make in terms of mistakes. So. All right, calendar. So we're going to be going over the test review today, tomorrow, and Wednesday. Thursday is going to be your Chapter 5 test. In a minute, I'll go over specific topics to be expecting, types of problems to be studying towards. Something I left off of this is Wednesday is going to be the due date of your recovery assignment. If you want to do recovery on the Chapter 3 test, there's a Teams assignment. I'll send out a reminder this afternoon. Just make sure you guys know where to go, where to look for that assignment. So that assignment includes test corrections. It includes doing some additional problems from the textbook, turning in your notes and homework for this unit, or sorry, for the past unit. And that's going to be due on Wednesday, so due Wednesday night. So the policy keeps changing slightly. So you can still recover up to an 89, but now you're eligible for it if you just make below an 89. So if you make it 85 and you want to try to improve your grade to 89, but it's not retroactive. So this is only for this test moving forward. And then the recovery test is going to be on Friday. You have 2 options, either 7:15 or 4:30. It'll be on Teams, but you need to turn all that in by Wednesday in order to be eligible to take that recovery test on Friday. Okay. Any questions about this week's calendar? Also, I'm going to start having just leading up to the test. I think there may be some students who may want it or need it. I'm going to have help sessions. So help sessions starting this afternoon, and I have 5th period lunch. So I'll have help sessions during my lunch period as well. So I'll make myself available through Teams, and if students want to come in, they can come in for help sessions, and I'll try to record them on Teams as well. So morning 7:30, lunch 5th period, and then after school from 3:30 to about 4. So, and I'll send out a reminder about that as well, so you know those help sessions are available. Okay. All right. Let's move to test topics. Okay, so this is on today's link as well. So we're gonna have 2 extended problems. The first one is similar to the one that we did on Friday, where you're given a function and you have to find first derivative. You got to create derivative sign line, find relative max, relative min, increase, decrease. And then we move to the second derivative function, right? All that messiness we factored out, we found the critical values, and then create a second derivative sign line, point of inflection, concave up, concave down. So that was a really long process. So on the test, it'll be either from f to f prime or from f prime to f double prime. So we saw the whole process on Friday, but on the test, you'll either see where I'm just asking you for min, max, increase, decrease, or I'm just asking you for POI, concave up, concave down. So if it's for concave up, concave down, I'll start you off with the f prime function, and then you'll find the second derivative and then gather that information. Okay, so we saw that on Friday. We probably won't see this problem today, but we'll probably get to it tomorrow and Wednesday. Okay, so the second is particle motion. This is also an extended problem with multiple parts. We'll do one of these problems today, where I give you a position function, and then you have to find first derivative and second derivative. And first derivative represents velocity. Second derivative represents acceleration. You create a velocity sign line, you create an acceleration sign line, and then using the sign lines, you can determine intervals moving left, moving right, motionless, or changing direction, increasing, decreasing speed, increasing, decreasing velocity. So we'll do one of these so you can see all the details involved there. The third type is being able to find derivatives involving the new rules that we learned. So if it's something where you have a messy log expression, you can expand it, right? Whether it's natural log or log base 3 or log base a. Expand out your log terms and then look to see what derivative rules you can apply. We have to make sure that we are comfortable and expecting all these the rules that we learned, right? We learned natural log, we learned base e to the x, we learned log base a, we learned a to the x or a to the u. So, and then within them, sometimes there's also a need for product, quotient, chain rule, depending on the structure of the problem. So I'm going to update this document. One thing I forgot to include for number 3 is one of those problems will be finding equation of tangent line. So after you find the derivative, you're going to find the slope. From the slope, use the order pair to get your tangent line equation. So I will update this document with that. And then you'll see a problem where you have to involve implicit differentiation. Maybe expansion, maybe product rule, maybe quotient rule involved there as well, but implicit differentiation. And we'll do a problem like that today. Log differentiation. Log differentiation is where we introduce logs into both sides of the equation because we see that the problem can benefit from log expansion properties. So we introduce logs to take advantage of the properties, and then we find the derivative that way. Right. And then finally, finding the derivative of inverse at a point. We didn't get to this problem on Friday, so I'm going to start off with an example like number 6. Okay, so Thursday's test, open notes, bring your calculator. Any questions that you guys have right now about the test? No questions? Everything seemed pretty clear? Okay. All right. So if we can turn to the worksheet that we ended on Friday, it's the 5153 natural log properties and derivative worksheet. We skipped the whole problem, a lot of problems from the front page. We just did number 6. And then we also did number 9 on the back, right? Number 9 was where we did, where it was a log differentiation problem. And I want us to look at number 12. So number 12 is find the derivative of inverse at a point. And as we go through number 12, I'm going to highlight the steps that we're going to take. And these steps, you can find this on that summary notes worksheet. So you don't have to, that summary page. You don't have to write all this out if you don't want to. You can kind of just access that later and print that out at a later time. But I want to kind of go through each step along the way, make sure you guys are clear. So here, the first thing that we have to recognize is that the value that's given to you in the problem is the x value of the inverse, but it's really the y value of the original function. That's what we have to, because f of x is what we're working with. You have to recognize that the number given to us is not the x value of the original, it's the y value of the function. So the problem may be asking for this. It's asking for the derivative of inverse at 11. So we're trying to find so even though this is sitting as the x value of the inverse, for our purposes, it's going to be the y value of the function, because everything that we're working on is on the function side of things. Even though in the end, we're going to be using that to evaluate the slope of the derivative of the inverse. So because we have the y value of the function given, we're going to set the function equal to the y value and solve for x. That's the first step. So we're going to put 11 in for the y location, right? We don't want to put 11 in for the x because that's a mismatch, right? We don't want to. So 11 goes in the y location of our function. And now we're going to work towards solving for x, because we need that information to move forward. Okay, I'm going to bring the 11 over to the right side so that I can get the 0 to show up. One thing is that this is not factorable, right? We can't, there's no GCF, this is not a quadratic function. So we're going to have to go through a guess and check to figure out what is the x value that's going to make this work. So that sounds like a tedious process, but it's going to be a number that's easy to find. Okay, so try 0. If 0 doesn't work, then try 1. That doesn't work, then try -1, then try 2, then try -2. Okay, within a few numbers, you'll be able to get to, you get that x value. So let's start with 0. Is 0 going to make this statement true? 0 minus 0 minus 10. -10 is obviously not equal to 0, so that doesn't work.
No.
Okay, how about 1? 2 minus 3 is -1, -1 minus 10. Okay, that's nowhere near 0. -1? 2 times -1 cubed, that's -2 plus 3, that's 1 minus 10, still not going to be equal to 0. Okay, what about 2? So 2 times 8 is 16. 16 minus 6 is 10. 10 minus 10 is 0. So I think this works, right? Okay, so that's the process you're going to go through. Guess and check. A couple of numbers in, you should be able to get to what that order pair is. So this is what we're after. We want our x value that's going to help us is going to be the 2. Okay, so we solved for x, we did guess and check, and now we're ready for our next step. Any questions up to this point? Okay, so next we're going to find the derivative. So f prime, what's f prime equal to?
6x squared.
Minus
3.
3. Yeah. Okay, this is our slope finding formula. Now you see the reason why we need that 2, right? The 2 is going to help us find the slope. Okay, what's our slope reduced to be? Two squared is 4. 4 times 6, 24 minus 3.
21.
Okay. So this is not the answer, but it's related to our answer. So just to give you a visual, well, let me read the steps first. We found the slope, and now the derivative of the inverse at its corresponding point is going to be the reciprocal of the slope that we just found. Okay, so let me give you a visual so you can have a picture in your mind here. What we found was for a certain order pair on the function, we found the derivative, we found the slope, and we found the slope to be 21. Okay, so if the slope of this graph is 21, then on the inverse, which is on the other graph, but it's at a corresponding point, the slope is going to be, that's right, just reciprocal. Don't change the sign, just flip the order of the numerator and denominator. So because 21 is really 21 over 1, we're just flipping the numerator and denominator around, getting 1 over 21. Okay. Any questions about the process? Any questions about the steps? Okay. So you'll see a problem like this on the test. Are we comfortable with this? Okay. All right, no questions? So let's move to our test review worksheets. First problem is tangent line equation. I'm going to skip that, come back to it later. Number 2 is similar to f prime sine line, f double prime sine line. So we'll skip that. And then let's look at a particle motion. It's been a while since we've seen particle motion, so let's do that one. This is number 3. Okay, so the problem says along the x-axis. So think about a particle moving along the x-axis, right? There's only 3 things it can do. It can either remain motionless, move to the right, or move to the left. Okay. At any time t is greater than 0, its velocity is given by v of t. So this one's a little bit shorter in the sense that this problem already gives you the velocity function. But on the test, I'll give you the position function, and you have to work your way to the velocity and the acceleration as well. So we're just going to start off with the velocity here. It's given to us. How do we move from velocity to acceleration? It says for part A, write an expression for the acceleration of the particle.
Find the derivative of the velocity equation.
Good, right. Velocity is kind of already at the f prime level, so we're going to move to the f double prime level, which is acceleration. Good, so we're going to find the velocity, find the derivative of velocity. What's involved here to find our derivative?
Product rule.
Good, product rule. Right. I think most students don't struggle with product rule, right? I think the struggle is recognizing the need for product rule. Sometimes it just kind of flies under the radar. You can't, if we're not actively looking for it, sometimes we just miss it, right? And that kind of throws off our process. So we need to just be able to recognize the need for product rule. Okay, what's f prime?
1.
Just 1, right? F and g stays the same. And now we're moved on to g prime. What's natural log t's derivative?
Would it be 0?
Well, this is this is u prime over u, right? Natural log of t is u prime over u, so 1 over t.
I thought the log included the t minus t.
Oh, okay, yeah. So these are separate. These are separate. So it looks like this. If the t and minus t are together, the problem will have to put parentheses around it. Otherwise, yeah, if you don't see parentheses, we have to assume that this is something outside of the natural log. Okay. How about minus t? What is
Minus 1.
minus 1? Yeah, it looks like a 1, but it's actually a t, right? If there's 1, it will go to 0, but it's t, so t will go to 1. Clean up here. T times 1 over t becomes 1. 1 minus 1 is 0. Okay, we'll revisit this in a little bit later here, but we have our answer for part A. We have our acceleration function. Okay, part B. For what value of t is the particle moving to the right? So what do we involve here for part B? Are we going to be using the velocity or the acceleration function?
Acceleration function.
It says movement to the right.
Oh, velocity.
So, yeah, that's just velocity, right? That's just velocity. So we're actually going to be gathering more information than what part B is asking for, because we're going to create a velocity sign line. If we can create a velocity sign line, then anything that is related to velocity is just right there in front of us. Okay, so how do we begin our velocity sign line? We first need to look for what?
Critical points.
Yeah, and how do you find critical points?
Set
Yeah.
function equals 0.
Good, set velocity equal to 0. Right. Those are the values that's going to kind of anchor our sign line. Right? What would you do next? Is there something that we can factor?
We can factor out the t.
Factor out the t. Okay. We have factored form, so we have two places that we can set equal to 0 to solve for t, right? So this part is done. We already have that critical point. Now let's move on to the other statement. Natural log of t minus 1 equals 0. I'm going to set them equal to each other. Okay, so we have to understand that this is not natural log times t, right? This is natural log of t. T is stuck inside natural log. So I want to solve for t, but how do I get that natural log to go away? Yep. If we involve the inverse, right, we know inverse is going to handle the natural log for us. So the inverse of natural log is e. So if I raise both sides, base e. E to the natural log will go away. I'm just left with t. E to the first power is just e. So we have our two critical points here, 0 and e. From here, we can move towards our velocity sign line. What does our domain statement say about our?
It starts like time goes past 0.
Good.
It's just 0.
Starts at 0, right? So we want to make sure you put 0 at the end, right? There's nothing that's going to be to the left of 0 because they're telling us t is greater than 0. And also, just within natural log itself, right? Natural log can't take any negative numbers, so it's going to have to be 0 forward. Good. Okay. Now we're ready to identify some test points. So between 0 and e, I can choose, I know e is around 2.7, I can choose 1. 2, but I think 1 is easier to plug in. I can choose anything to the right of e, so I can choose 3 or 4, but I like to choose something in terms of e because it allows me to evaluate quickly without having to go to my calculator. Because natural log and e is just going to work itself out to something easy to interpret. Okay. We're going to test against the factored form of the velocity function. We just want to know whether it's positive or negative. So 1 goes in for t. That's positive. Natural log of 1, that's 0. 0 minus 1 is negative. Negative times positive is negative. Okay, I'm going to test e squared against my velocity function. So that's e squared times natural log of e squared minus 1. I can bring that 2 down in front because this is now part of a log property. Bring that 2 in front, 2 times natural log of e, that's 2. 2 minus 1 is positive. Positive times positive is positive. So what do these mean? This negative interval tells us what's happening. Okay, good. That's changing direction. What's from 0 to e? What can you say about the object?
Moving to the
Left. Right, move to the left. It's because it's going along the x-axis, right? Horizontal, so either left or right. Now, sometimes you may see a problem where it's along the y-axis. If it is, then positive velocity is up, negative velocity is down. And then here is moving to the right. Okay. So we can answer our question now, right? Everything that we need is from the sign line. For what value of t is the particle moving to the right?
Everything greater than e.
Sorry, say it again.
Everything greater than e.
Yeah, so you can say t is greater than e. I like to put it in interval notation, so I like to say from e to infinity. Notice that when you write your interval, you don't include the test points, right? The test points is done. We don't look at those test points anymore, just your critical values and infinity. And what's our reasoning? What's our because statement? Good, because velocity is greater than 0. Okay, part C. What is the minimum velocity? So another word for minimum velocity is basically when the acceleration change signs. Okay, that's where we can find minimum velocity, where acceleration changes sign. So what that really is telling us to do is we're going to create our acceleration sign line, just like how we did our velocity sign line. So we'll set our acceleration equal to 0. Just like before, I want to solve for t. T is stuck inside natural log. Raise both sides, base e. E to the 0 power is 1. And then e in natural log goes away, so t is equal to 1. So here's my acceleration sign line. Is there another value we should put onto the acceleration sign line? Yeah, it's a starting point, right? It's nice to have a starting point here. Right. Choose values, test against the acceleration function. I'll choose 1/2. And to the right of 1, I can choose 2, but I like to choose something in terms of e to make it easier. Back into my acceleration function. So 1/2 in for natural log of t, natural log of 1/2, that's a negative value. You can look at the graph of natural log, convince yourself of that, or you can plug in the calculator. But natural log of 1/2 is going to be somewhere here, right? So definitely negative. If I plug e in for t, natural log of e, is that positive or negative? Positive, yeah. So it says minimum velocity occurs at t equals 1 because our acceleration changes from negative to positive. So we know where the velocity occurs, but it's asking for the actual velocity. So how can we find the actual velocity? Yeah, plug 1 into the velocity. Yeah. Natural log of 1 is 0. 0 minus 1 is just negative 1. Oops. I want to extend this a little bit longer into something that we may see on the test as well. So if you guys can include part D. And for part D, if you guys can write this down, is the speed of particle increasing or decreasing at t equals 3? So do you guys remember from chapter 2, how do we increasing, decreasing speed for a particle?
Look at the velocity is constant.
That's part of it. That's part of it. Something else. We also have to involve what? Yeah, get involved. So do you guys remember what do we do with acceleration and velocity? Yeah, either same signs or opposite signs, right? If they have the same signs, that means what? Increasing speed, right? Either both positive or both negative. But if one is positive and the other is negative, then it means decreasing speed. Okay. So I'm going to include this on the summary sheet that you guys can print out. So, but yeah, to determine increasing and decreasing speed, we compare signs between velocity and acceleration. Okay. If they both have the same signs, either both positive or both negative, increasing speed. If one is negative and the other is positive, then decreasing speed. So let's use that knowledge to help us make our conclusion. So 3 is to the right of E, so we're looking at the sign here. And 3 is to the right of 1, we're looking at the sign here. What do you notice? Both positive, therefore speed is increasing. Yeah. Okay, part E is the velocity of the particle. Is the velocity of the particle increasing or decreasing at t equals 1/2? So the wording is virtually the same. I'm just changing one word, which is affecting how we interpret. So do you guys remember, how do we interpret that? Where do we look to determine if the velocity is increasing or decreasing? Any ideas?
And the acceleration.
Yeah, it's acceleration. It looks like it's velocity, but it's actually acceleration. What is it about the wording that tells us to look at acceleration and not velocity? Yeah. Yeah, this is right. Increase, decrease. This is not the same thing as saying is a velocity positive or negative, right? This is velocity increasing or decreasing. This is indicating something else. This is talking about the rate of change now. It's changing what it's really referring to. It's the rate of change of velocity. And it's really the slope of velocity, which is really acceleration. So to determine increasing, decreasing velocity, we just look at the sign of acceleration. If acceleration is positive, then velocity is increasing. If acceleration is negative, then velocity is decreasing. It's understandable, a lot of us want to look at velocity, but that increase, decrease changes what it's referring to. Okay, so what can we conclude here? Yeah, acceleration is negative, right? At 1/2, my acceleration is negative. Okay, questions? Okay, so this is the type of flow that you're going to be expecting on the particle motion problem. Okay, maybe we'll do another one, but at least feet wet, we can kind of get more comfortable over the next day or two. Okay, let's look at number 4 and 5. Let's finish off with those two, with these two problems here, 4 and 5. Okay, does anybody still need to look at number 3? Okay. Okay, here's number 4. We want to find the derivative. Two things. Can you guys point out what specifically we have to involve here as we find the derivative? Good. Product rule. Okay. And implicit. Good. Product rule, because y and natural log of x are connected by multiplication. There are two separate things. We have to involve product rule. Implicit, because you have multiple y's in the equation, right? The y's and x's are not cleanly separated. All right, so let's see if we can fill these in here. What's f prime? Good, dy dx. Well, 1 times dy dx, right?
Yeah.
Okay, good, yeah. Okay, g function, no changes. Back to f, no changes. Okay, what's g prime?
1 over n.
Yeah, u prime over u, 1 over x. So we took care of that part of it. What about y squared?
It's 2y dx.
Good. We took y's derivative, and we have to involve dy dx. Equals 0. Okay, careful with this side. I know right now it's not really hard to do that, but if that's a different number, we're also going to make it go to 0. So if it's 12 or 6 or 8, you got to make it go to 0. We don't want to keep that constant, right? That constant is also being impacted. We'll go to 0. Okay. This is the only calculus step we have in the problem. The rest is just cleanup. Okay, questions here? Okay, we'll move to our cleanup. One thing I want to point out, something I like to do to just quickly confirm that I'm on the right track, is I want to make sure that I have the correct number of dy dx's, right? Sometimes it's easy to lose track. So I look at my original equation and I ask myself, how many y's do we see in my original problem? I have 2 instances of y's, so I should have 2 dy dx's that pop up. It's a quick way just to confirm I don't have too many, or I don't have, you know, one too many, or not enough. Okay. Have the dy dx terms on one side, the non-dy dx terms on the other side. I'm going to just combine that to be a fraction there, make it negative y over x. Factor dy dx out. Divide both sides by the parentheses. Either leave like that, or I recognize that this x and this natural log of x plus 2y, they're both kind of in its own separate denominator space. So I just kind of make them all, both of them share the same denominator space. Okay, either is fine. Okay, one last one, number 5. We want to find the derivative. What can we do to rewrite this problem? Okay. Let's see. 1/3 what though? Yeah. Okay. X over 3 or 1/3 x. Right now I'm going to start off as x over 3 to kind of make sure we see that the x is in the numerator, the 3 is in the denominator, and then if you want to make it easier to read, we can convert that to 1/3 x. All right. Now, there's something about this problem that requires a very specific method. Do you guys see what is needed here? Okay, so this is not something that we can apply using power rule, chain rule. And the reason why is because we have a variable raised to a variable. Right? This is not the same thing as a variable raised to a constant, right, where we can go through power rule. So this is not going to be a power rule problem. And so there's an issue here. We don't have a specific rule that can handle a variable to a variable. So we have to find a way to work around this issue, present this in a different form. Yeah, so that's the idea. The idea is that this exponent variable is causing issues. Good. We want this exponent in a different location. We want to bring it down, but to bring it down, we want to involve logs. So this is what this is a very specific method called log differentiation. So let me talk a little bit about that. Log differentiation is where you look at a problem, there's no logs in it at all. You look at the problem and you say to yourself, this problem could really benefit from log properties. And so we introduce logs to both sides of the equation, expand using the properties, and either it'll make the problem easier or it'll produce it into a form that we can actually apply a rule for. So this is an instance where we don't have any other method to solve this, so we have to find a different form of this problem. So we take the natural log of both sides. And now I'm going to change it to 1/3 x. It just makes it easier when it comes down. It's going to be a little cleaner. So now we have a special property, right? Power property, right? That exponent can now be free to move in front. This is not a derivative step. This is just a rearranging step here. All right, look at all these steps that we took. No derivative. This is the same thing as this. It's just that this is a lot easier now for us to identify a derivative rule. So now we're going to find the derivative. Okay, a couple things that we have to involve here as we step into derivative rule. What do you notice? There's a need for what? Okay, yeah, so specifically, yeah, we definitely have to involve power rule. We definitely have to involve natural log rule. Something else, though. What else is needed? All right, this natural log of y here. There's a little bit of what going on here. Chain, but also, well, you see, y is not by itself, right? So there's a little bit of, yeah, implicit. Okay, so I want to just make sure we I mean, it's not a huge implicit, but it is a little bit because that y is kind of not by itself. We have to, there's a dy ds is going to pop up. And something else, how about on the right side? Something that we have to be aware of. There's a need for what? Do you see it? Let me ask you this. How many functions do you see? It's product rule. Yeah, recognizing it is the hard part, right? This is not one term. These are two separate terms. We got to use product rule. Okay, so left side, natural log of y. What does that become?
1 over
Uh-huh.
dy.
dy dx, right? U prime over u, so that's 1 over y, but we just took y's derivative, so we need to include that dy dx. We're going to fill in our f prime g plus fg prime. What's f prime? Hmm? Back to f. Okay, what's u prime here?
15x
Over.
over 3 plus 5x.
Good. U prime over u. Okay, your derivative with law of differentiation is just going to be messy. Okay, don't worry about having to clean everything up. If you can get dy dx by itself on the left side, you're doing good. Okay, so how do we get dy dx by itself? Okay, divide by 1 over y, which is the same thing as multiply by y. So I'm going to move the y over to the right side. Okay, if you want to clean up, you can, but you don't have to. So we basically have the answer. There's one more thing I want us to do, though. Yeah. What can we replace this with? The original. Yeah. There we go. The reason why we do that is because we have a function to begin with. So if we have a function to begin with, we should be able to represent the derivative purely in terms of x. We shouldn't need to use the y. The y is kind of like a placeholder until we can represent our final answer. Okay, your answer is messy, but well, we have our derivative. Okay, questions? Good. So I feel like, we're able to kind of hit all the big topics between Friday and Monday, and tomorrow we can just go back, review these topics over again. I'll pick out the worksheet that I didn't get to today. We'll look at that, and which is, I think, the more we do repetition, the more comfortable we get. Hopefully by Thursday, you guys will feel good.
Mr. Yang, I have a question.
Yeah. Question?
So when you write the equation for the last time, when you rewrite y, do you not have to put it in parentheses and then put the x?
You're asking about this y here?
Yes.
Okay, can you say that again? I didn't hear you.
When you rewrite it, how come you don't have to put it in parentheses and then put the...
Oh, why don't we have to leave this in parentheses? like this?
No, just like underneath the root, like how they wrote it in the initial problem.
Underneath the roots.
Like in the initial problem, the way they write it, like cube root. Yeah. Yes, around the 2 and
Oh, you mean, why do we not have to rewrite this as to the 1/3, you mean?
No,
Oh, I'm sorry. I
yeah,
think I left something out, right? Okay, sorry, there should be an X there.
Yeah.
Sorry, yeah, it should be X here. Sorry. Yeah, go ahead.
Okay.
Yeah, sorry about that. Yeah, I meant to copy the entire problem over. I left out the X.
Okay.
Thanks.
Mr. Yang.
Yeah.
When you were combining the 1/3 x with the 15x squared over the 2 plus 5x cubed, why did the x go to the denominator? I thought it was in the numerator.
Oh, yeah, you're right. Sorry, guys. Made a couple mistakes here. Thank you. Oh, great. Thanks so much. Awesome. Yeah, sorry about those mistakes, guys. Yeah, so there should be X here, and then the X from here, that should be in the numerator, not the denominator. But if you want to leave all that in this form, you can. There's no need to go as far as I did, or you can go even further if you wanted to. Okay, sorry about that. Anything else? All right, have a great day, guys. I'll see you tomorrow. We'll have tomorrow and Wednesday to review. If you want to do recovery, make sure you start working on those assignments, and I will send out a reminder this afternoon. Okay, health session, 5th period, and also after school starting today and before school tomorrow, 7:30. Okay, have a great day, guys.